Greetings, folks. This is part 2 of our descriptive statistics lecture. This is the one where we need to introduce the math, okay? So it's going to be kind of a short lecture where I want to talk about each of the different measures that we will be calculating, each of the individual statistics or parameters that we'll be calculating. And then in a follow-up video, I'll show you exactly how to go through a real data set step by step to calculate each of these measures. Okay, so to start out, remember that we've been talking about descriptive statistics whose goal is to organize data, to show you patterns in data, to show you where the data groups, if you will, right? And so one of the best ways of doing that is to look for these so-called center points in the data. It might not be right in the center if it's not a normally distributed or symmetrical distribution. It might be skewed to the left or the right where that big high point is. We looked at a bunch of different shapes of distributions at the end of the last lecture. But in either case, the measure of central tendency that you calculate, that goal of that measure is to give you the best idea of where the center point is for those data. Now usually, especially in a symmetrical distribution where you have an equal number of scores above and below the mean, then that center point, the best center point, will in fact be the mean. So if you look at like the normal distribution here, normal distributions are symmetrical, right? So the very center tall point of that distribution is the mean, the median, and the mode, right? It is the most frequently occurring. As you can see on the y-axis, it goes the highest up there in frequency. It is the median because it has an equal number on both the top and the bottom, and because they are spread in the same way, they have an equal impact on that center score, and so the mean, median, and mode are all the same thing in a normal distribution. But if your distribution is skewed, like you have a ceiling effect or a floor effect, and you have this tail that goes off in one direction, that extreme score, so imagine a situation where most of your scores are at the low end of a scale. So everybody did, let's say, mediocre or even poorly on an exam. But one student cheated, and they ended up with 100, a perfect score. That extreme score relative to this bunching down here is going to have a huge influence on the mean. It's something I'm going to show you as we move along. But it won't have the same influence on the median. That's because of the way that the different variables here are calculated. So let's walk through them and let's see how we calculate each of these. We'll start out with maybe not the easiest, but certainly the one you are most familiar with, the mean. Right? You probably called it the average your entire life, but it is also referred to as the mean. It is simply the arithmetic average of a group of scores. So remember that we are talking right now about populations. Now, I don't care too much at the very beginning of the semester if you go back and forth between using, let's say, x bar versus mu, even though x bar is technically supposed to be reserved for when we talk about statistics, only samples of data, and mu, the Latin character, is only supposed to be used for populations and parameters. Right now, it's less of a concern, but we are, in fact, working with populations, so that's why the way I'm going to show you these formulas. So mu, the mean, is equal to sigma x, so that big Greek character that looks like a fancy E is called sigma. That's uppercase sigma, and it means the sum of. So in this case, because x is in parentheses, it's saying the sum of all of the x's. So x's are your individual raw scores on that variable x. So whatever your variable is, let's say the height of people in our class. This is saying sum all of the heights. So add all of those heights together, and then divide by n. In statistics, n refers to the number of individuals in that population. Lowercase n is for samples, number of individuals in that sample. Okay, so it's really easy. You've done this a million times. You add up all the scores, you divide by the number of scores, you get the mean, you get the average. Now, we're always going to work with 2 decimal places for our final answers, so remember that when you're doing your homework, you're doing your calculations on the exam. Don't go to 3, 4, 5, 6, 7 decimal places, truncate them all at 2. Okay, that'll just make sure that the math that I do by hand matches the math that you're doing by hand, and that if you make an error, I can more easily identify where that error is. Okay, so the mean. Maybe easier than the mean to calculate, in fact considerably easier than the mean to calculate, is what we might call the median. So you've heard of medians before, right? The median in a road, for example. So if you look at that highway up there, you've got a bunch of roads, or a bunch of lanes going one direction, a bunch of lanes going another direction, and in the middle you've got this dividing point. And at least typically that dividing point is such that you have an equal number of lanes on either side of that median. Well, the median's the same thing when it comes to data. It's the center score where you'd have an equal number of scores that were greater than that one and an equal number of scores that were lower than that one. So the first thing you have to do when you calculate the median is to take that mass of raw scores that are probably unorganized and organize them from lowest to highest score. Okay, so if you look at that very first row, that 5, 3, 6, 9, 11, 28, 3, 1, 15, okay, they are all out of order. But if I reorganize them into the row right below them, I have the exact same scores. They're just put back in numerical order. Now notice, the score 3 occurs twice. Actually, I put 3 fingers up. Twice in that data set, right? In that raw data. So when I reorganize it from lowest to highest, I still have to write the 3 2 times. Because that would represent an individual or a trial where somebody got that particular score. Okay, so you can't simply get rid of it when you reorder them. And it's an error that I do frequently see among some students. So make sure you're paying attention to that. Okay, so now it's reorganized. Now we simply have to find the middle score, the one that divides the distribution in half perfectly. So in this particular case, we have an odd number of scores. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9 scores, which means the middle score is going to be that number 5, right? Where you've got 4 below it and 4 above it. So that's real easy. It's the 6. So in this top data set, the median is a 6. What about the bottom data set? So it starts out unorganized, we reorganize it. Now there are only 8 scores here. There isn't a score in the middle that we can identify as the median. What do you think you do here? Well, what you have to do is identify the 2 scores then that represent that middle point. You have to add them together and find the center point between them. So you add them and divide by 2, and you get 21.5 in this case. So the median of that bottom set of data would be the 21.5. Make sense? Okay, median is also sometimes referred to as the second quartile. So the 50% mark through there, right? 50th percentile, in fact. That'll become relevant later because we'll calculate other quartiles. Mode. Definitely the easiest of all your measures of central tendency, and it's the last of our measures of central tendency. It is simply the most common score of all the scores in a sample. So I just grabbed the same data from the first example for median, and I reorganize it again, right, so that I can see them from lowest to highest. It allows me to more easily see when a score repeats. And we see that in this particular data set, only 1 score ever repeats, and that's the 3. There are 2 of them. Every other value occurs only 1 time. So the mode for this data set would be 3. Sometimes with greater numbers of raw scores, you might have a couple of values that occur most frequently. So let's say there was another 11 in here. Then you'd have 2 modes because both 3 and the 11 occurred twice. In this case, you list them both, and it's what we call a bimodal distribution, right? So instead of a camel with 1 hump, you've got the camel with 2 humps in that distribution. The frequency is the highest for 2 scores. It can be more than that. You can have 3, 4, 5 scores, but we don't tend to call them trimodal and quadrimodal. We just sort of adopt the name multimodal at that point. So when you look at distributions of scores, and you're looking at a score that might be fitting with the pack versus away from the pack, as sort of the central tendency is supposed to indicate to you, you might see what we call outliers. An outlier is simply an extreme score that doesn't seem to fit with the rest of the data. So this is a very contrived example on this image here. But you imagine you collect a bunch of data and they all line up, all these individual dots line up very closely along this sort of curved line that might predict some relationship between the x and the y variables. But then there's this one dot way off to the side, one trial or one person who performed very, very differently from the rest, right? We'll see later on some sort of made-up graphs. We talk a lot about how the number of hours spent watching TV is negatively correlated with the your grade in class. Probably because if you're spending too much time watching TV, you're not doing your homework, right? But then there might be that one student who spent, 30 hours a week watching TV and still got 100. They would be the outlier there. Outliers are interesting for a number of reasons. So we oftentimes engage in outlier analyses. There's a formal outlier analysis that requires a couple of calculations, but a more informal outlier analysis means simply looking into that particular data point. It may be the case that, say, I was recording ages for the class, and every time you told me your age, I wrote it down. Then later on, I entered it into a spreadsheet so I could analyze the data. And when I entered your age of 19, I accidentally hit the 1 twice, and I put in 119. That typo will result in an outlier in the age that I can then go look at and say, okay, that was a mistake on the experimenter's side of things. Sometimes there may be some other mistake that occurred that resulted in this outlier. And then at other times, it may be something that's theoretically interesting. So say that student who decided they were going to watch a ton of TV, but then also aced the exam. Looking into that, you might find that the ton of TV that they spent was actually all YouTube tutorial videos on material related to class. And then you could say, okay, there are exceptions. It's not just that TV hurts performance, it's that TV not related to courses hurts performance. And so my point is that outliers can be extremely interesting theoretically at times, or they could be simply revealing of an accident. But it's important always to look at those outliers. Now let me put a caveat on before I go on to this anymore. In this class, I may ask you at various times to identify if there is an outlier in a data set. That is, I may want you to look at the distribution and see whether or not there's an extreme score that's very low or very high compared to the rest of those. But let me be clear, I do not want you to remove any extreme scores when doing your calculations. Leave them in, that way your calculations look just like my calculations because I'm going to leave them in. Okay? So what do outliers do to these measures of central tendency? If one data set is not normal and is skewed in some way, I told you that maybe the mean might not be the best measure, and that's because of the way outliers affect that average. So in this case, we have just 5 scores, okay? 5 individuals that took a standardized test that goes all the way up to 1,500 points. We see that most of these individuals, so 4 of them, their scores fell between 800 and 950. Right? You can even see the mode would be somewhere between 900 and 950. But then one student scored way up in the 1400 to 1450 range. Right? Might be called an outlier. At least visually looks like it doesn't sit with the rest of them. It's like a crowd of individuals eating lunch and one person 20 feet away eating at a park bench by themselves. Right? They're the outlier here. So what's the average of all of these data? In this case, these are fake data, of course, 991.2. But what happens if we were just to remove that one score, that one outlier? You bring the mean down good 4 points here, right? The average drops considerably because of that one individual score. Excuse me, I say 104 points here. That average is now much closer to the pack of scores. So if you look at where the blue arrow is in the top figure, that arrow that is supposed to be the central point of our data is in fact higher than 4 out of 5 of our data points, 80% of our data. It's not a very good center point in this case. Below, when we remove the outlier, we see that that has a different effect now, and that average goes right down into the pack of scores, right? It looks more like a central point. So what happens here? If I tell you you can't remove the outlier, then what's a better way of depicting the center point of these data? Is there another measure that's not affected by extreme scores? So if you look at a data set like this, right? Unorganized, then it gets reorganized. The mode is 2, the median is 11.5, the mean is 24.29. Now, one thing you'll notice, if I were to add in an extreme score here, just like in the past case, so let's say I added in a 200. If I add in that 200, it's going to dramatically move the mean higher to shift that center point to account for that extreme score of the 200. But if I look at the median doesn't care how high or how low you are above or below the mean. It's simply that you are on one side or the other. So adding an extreme score on one side simply moves the median over one score. It doesn't dramatically affect the median. So in highly skewed distributions, the median is frequently one of the better measures that we can use. We can skip over this example. I think I've made that point about how the median versus the mean may differently reflect the center point of a distribution. And it's up to you to think about how that distribution might be skewed and whether or not the median might be that better representation. Okay, so those are your measures of central tendency, where the center point is. So after you establish the center point, how does the distribution spread out from that center point? That's the other thing we need to know, not just where the middle is, but how far on either side does the distribution really go? Are there a bunch of scores right near the middle? Or are those scores really spread far from the middle, such that there's really not a very good center point? The distribution's really wide, and people are very different in this ability or this personality characteristic. Well, in order to determine that, we calculate what are called measures of variability. One of the most simple measures of variability simply takes the very lowest score in a data set and the very highest score in a data set and subtracts the lowest from the highest. So say you record temperatures every day, on your back porch throughout the year, and the hottest day we had this year was a 98, and the lowest day we had this year was a 13, right, for highs. You just simply take the 98 minus the 13, take your 85 resulting range there, and that is the entire spectrum of values that your data set encompasses. Doesn't tell you a whole lot, but does tell you the absolute spread. It's good for calculating a couple of other different things that we'll see. It's good for then creating your graphs, right? If you're going to visually display some data, you need to know the range so that when you go to plot a score, it's on your graph and not off of it because you didn't know what the range was. And so it can tell you some useful information, but what it doesn't tell you is really how far from the average the typical score is. There could be one extreme in either direction, right? You get a day where it was 1 and a day where it was 120, but all the other days were between 50 and 84, right? Or something like that, right? The range does not give you that indication. To get that kind of information, we need to calculate another measure of variability. And these two measures of variability, actually, that I'm going to introduce are fundamentally the same. One is simply a precursor to the other one. So variance and standard deviation. What do they mean? So I'm going to take standard deviation since that's the one we talk about more. It's basically saying that any score in a data set is likely to differ somewhat from the average. Right? You might be slightly above average on something. You might be slightly below average on something. You might be really highly above average on something or really way below average on something. What variance and standard deviation does is it calculates how far above or below average each individual score is, so we can see how far away each score is, and then it averages that to get an idea of, on average, how much do scores vary from that mean. How far are they spreading from that center point on average? Okay, so to calculate it, we first started by calculating variance, right? Variance can be referred to in a lot of different ways here, depending on whether it's APA style or the conventions that we'll use in formulas. So APA style typically uses an SD, which is standard deviation, with the superscript of a 2, so SD squared. That's because variance literally is standard deviation squared, or you could say it otherwise, standard deviation is the square root of variance. When we write it in formulas, when we talk about samples, remember we use our Latin characters, so s squared. When we talk about populations, we use our Greek characters, so lowercase sigma squared. Notice that the standard deviation symbols are identical, just simply without the squared, without that 2 superscript. Okay, so let's look at these formulas, and then like I said in the next video, we'll talk about how to use them with a data set. So, variance. What is variance doing? Remember, we're trying to figure out how far each score spreads from the mean. So let's look at the numerator right in the parentheses there. We see an x minus mu. X is the score, an individual raw score, your score, my score, Bob's score. Subtract the mean from that. That will give you a number that represents how far above or below the mean that score is, right? If you were a 20 and the mean was 16, then you'd have a positive 4 in that numerator right there. If you were a 12 and it was a 16, you'd have a negative 4 in that numerator. Each one representing that you were either 4 above or 4 below in raw score points from that average. Okay, makes sense? Now, because some of those are negative and some of those are positive, depending on whether the score is above or below the average, if we tried to add them together to get an average right now, some of them would cancel each other out. So what can you do to a negative score to turn it into a positive score? You square it, right? So now each of those deviations, the x minus the mean, how far it deviates from the mean, each of those is going to be squared, right? So you take your negative 4, you square it. Take the 4, you square it. Take all those other values, you square them up. Then we see that sigma on the outside of the parentheses. This means it's time to sum them all together. So add all of those squared deviations. This part of the equation, that numerator, is oftentimes referred to as the sum of squares, right? We'll talk about it a little bit of sum of squares now, but we're going to bring up that concept later on because we're going to start using sums of squares more independently in future formulas. So we get all that, we get our sums of squares, and then we divide by n, the number of scores in that population. After that, you have variance. That's it. Now, most of the time, we're going to use standard deviation in later calculations that we do. And so once you get variance, you simply take the square root of that end product, and you have standard deviation. So it's really, really quite easy. Here are the sort of foolproof steps, right? Find the average, subtract the mean from each individual score, square each of those numbers, sum all of these squared numbers into the sum of squares, divide the resulting number by the number of scores, and if you're calculating standard deviation, take the square root of that number. Okay, pretty straightforward, but again, let's look at an example in the last video so you can see how exactly to do it. And then in your homework, you're going to do it and get practice at it, because if there's anything you're going to do a lot in this class, it's going to be calculating standard deviation. In fact, you're going to do it so much at the front end that you're going to show me how good you are at it, and you're going to prove to me how good you are at it, that I won't make you calculate it anymore moving forward. I'll just provide you with that information so you can work on the more interesting, fun stuff. Okay, what's another measure of variability that I said we could calculate? Well, when you calculate the median, remember the median is halfway between the lowest score and the highest score. So really that is the 50th percentile, where 50% of scores fall at or below that value. This is sometimes referred to as the second quartile. Quarters, right, are quartiles, percentiles. This is just the 25th percentile. And then each other quarter. So the 25th, the 50th, the 75th, the 100th. The 100th percentile is obviously the highest score. The 0th percentile is the very lowest score. The 50th percentile, the second quartile, is the median. Now what we have to figure out is the 25th and the 75th, what are called the first and third quartiles. Okay? And really all you have to do is, once you've identified the median, if there's an actual score, so you have an odd number of raw scores so that one particular value stands out as your median, then sort of mark it out with your marker and pretend like it's no longer part of the scores, and now look at the ones on the left-hand side and find the center point. Now look at the ones on the right-hand side and find the center point. Okay, if it was an even number of scores and you had to create one, then there's nothing to eliminate. You just use all the remaining scores and find those two center points. Okay, so again, I'll walk you through an example to show you this. But the interquartile range then, super simple. You just take quartile 3, subtract off quartile 1, and what you get here is a range, right? It's just like range from before, but now it's for just the middle 50% of the data. It doesn't take into account those more extreme scores at the end. It says, where do the middle of the data range, right? What scores do they range between? Okay, so those are your measures of central tendency. Those are your measures of variability. Once you've done this, and you've sort of reassured yourself at how simple it is, I know looking at the formulas at the beginning, you're going, fuck, it all looks Greek to me. The stats joke, because they actually are Greek characters. You'll notice how simple it really is. And then that is the most difficult it will ever be all semester. I promise you that. So as long as you figure out standard deviation and you remember, please excuse my dear Aunt Sally, parentheses, exponents, multiplication, division, addition, subtraction, right? The order of operations. Remember that so that you can work your way through a formula and you're going to nail this class, right? It's easy. So let's summarize what we went over. Frequency tables. Turn those frequency tables into cumulative percentages or percentiles. Flip them on their side, create a histogram or a frequency polygon. Well, frequency polygon with a whole bunch of data starts to look like a big smoothed over distribution, and in many of those cases looks normal, bell-shaped. When it doesn't, well, that's when we start talking about kurtosis. Is it positively skewed, negatively skewed? Is it platykurtic, real flat? Is it leptokurtic? Or is it more bell-shaped and mesokurtic? Then we jumped into math, right? Measures of central tendency, mean, median, mode. Measures of variability, range, interquartile range, variance, standard deviation, and that's it. Really pretty straightforward, simple lecture here. I want you to concentrate more on concepts, understanding what standard deviation is, understanding how to create things like histograms and frequency polygons, and then working your way through the math of doing a standard deviation. Think about it a little bit like creating maybe a food for the first time from a recipe. You're probably not going to nail it perfectly the first time. You're not going to remember all the steps the first time. But after you've done it a handful of times, it becomes really automatic. That's where we want standard deviation to be. We want it to be so easy that you can work your way through the steps without even really thinking too much about it. Okay? So that's it. Remember the last video, we're just going to work our way through an example so you can see the math at every stage of the process. Okay? Excuse me. That's it. So you guys have a great day. Cheers.